So assuming that the force P is 60 kips and yield strength is 42 ksi, estimate the torque, assuming distortion energy theory. Okay, so first thing is, in order to find the torque, we need to first ask ourselves, which part of uh, the solid circular shaft is going to be uh, critically loaded, that is, the stress is going to reach its maximum. So in this case, turns out that the maximum stress is going to be all along the outer diameter of the shaft, right? It's going to be subject to, so it's here or there, wherever you like, it's going to have the same state of stress. It's going to have a normal stress due to P and going to have a shear stress due to torque. So if you, what's that? Shear stress due to torque and normal stress due to P. So if you take this element and assume that this is X, Y, Z, then this is going to be loaded like so. Okay, so the stress due to sigma, the normal stress is going to be, if you see the direction of this force, it's compressive. So the stress, and I've shown it to be tensile here. So it's nearly going to be minus P divided by A. And then the shear stress is going to be, well, it reaches maximum at the outer diameter. So it's going to be T, in this case, the radius is half the diameter divided by J.
What makes the P over A negative?
Compressive. Look at the direction of this force. It's downwards. It's compressing. Okay, so that's the stress. So let's simplify this. It's P divided by pi d squared divided by 4. That's the cross-sectional area. And then tau xy equals T d divided by 2. The polar moment of inertia is pi d raised to 4 divided by 32. So this is 16 T times pi d cubed. Okay, so we can sub in the value for P. It's 60 kips. D is, so P is 60. D is 1.5, that's given here. And so we can solve for sigma x. That comes out to be minus 33.95. It's going to be KSI, because I kept the value of force in kilo, in kips, right? And tau xy, which we'll solve in terms of torque, it comes out to be 1.51 T. Like T is unknown. Okay. Now that we have that, we can now apply the distortion energy criterion, which says that failure will occur when the von Mises stress is equal to Sy, or the yield strength in shear or strength, right? So this is, so two formulas for this. One formula is in terms of principal stress. The other formula for this sigma prime is in terms of sigma x, sigma y, and tau xy. So instead of finding the principal stress here, we just use the other formula, which is what I would write here: sigma x squared, sigma y squared.
Wait, when is sigma prime equal to like yield strength? Because I know that like sometimes when we calculate the factor of safety, it's sometimes the yield strength over the sigma.
Yeah, so there is no factor of safety here. The factor of safety is 1, right?
So if like we're not given a factor of safety, we assume that it's 1 and therefore those two
are equal, right?
Okay.
So this is the formula which is also in your formula sheet. There's the stress in terms of sigma x, sigma y, tau xy equals sy. And so some of the things cancel off. So this is 0. This will also be 0 because sigma y is 0. And so if we can write this as sigma x square plus 3 tau xy square equals sy square, and sigma x is 33.95, 1.51, 42 square. And so if you solve for t,
103.
oh, my bad, 3 is here, doesn't go away, and you get torque equals 9.45 kip inch. Okay. Okay, last problem. So a stepped steel shaft shown below has dimensions of uh, d divided by d. So from that and this information, you can compute capital D if you want to. And then the radius of the fillet is 3. The surfaces are machined and the steel has an ultimate strength of 70 MPa. So let's write this down. D divided by D is 1.2. Small d is 30. R is 3 mm. And ultimate strength is 700 MPa. Yield strength is 550 MPa. And endurance strength is 239 MPa, and that is corrected. So you don't need to compute the corrections by finding Ka, Kb, and so on, because you're given that's fully corrected. The rotating shaft used in the spur gear reducer is subject to constant bending moment and steady torque, which results in a calculated stress of 60 MPa in bending and 80 MPa in torsion. Okay, so now the torques are told to be steady. So the torque on this is 80 MPa. Okay, and that is going to be the steady torque because it keeps the thing rotating. It's also subject to a steady bending load of 60 MPa. So this axis are along the shaft, while the axis of this bending moment is in this direction. The arrow gives you the direction of M. Maybe I should draw it this way. Okay, so this moment is also constant, but the thing is that because this is, well, I think I did a, oh, so my bad. So this is already in terms of stress. So I shouldn't put T there, I should put tau. My bad. This should be tau M, right? Not T, because the units of T is Newton meters. Okay, so then it's also subjected to a bending moment, which leads to a stress sigma. This should be sigma, and that is 60 MPa. Okay, now the question is it alternating stress or it's the constant stress of sigma m? So even though sigma is a constant, you're told that it's a steady, constant bending moment. Because the shaft is rotating, you'll see that uh, it actually turns out that the top part is going to be stressed sometimes in compression, sometimes it's going to be in tension, which means that this stress is actually the alternating stress and not the uh, steady sigma m. Okay. So sigma A, and let me put a bar over that just to distinguish it from the stress, which I need to compute by taking into effect the stress concentration here. So sigma bar is 60 MPa and tau m bar is 80 MPa. Okay, so that's all what is given. You're also told that in these are nominal values, do not consider stress concentration factor. So what we need to do here is we need to find sigma A by taking the stress concentration fatigue and multiplying with nominal, and then for same for M. So Kf, the corresponding one is Fs in shear. So okay, so we need to find Kf, Kfs, that's not given. Okay, now the questions are determine the factor of safety with respect to infinite life using D. Goodman, and factor of safety using first cycle yielding. Okay, so what we need is, so part one, is it AA? We need to find NF, where NF is given by the formula sigma A prime SE plus sigma M prime SUT. I think that's right. Right? We asked to find NF. And then the second part, we asked to find NY, which is SY divided by sigma max, where sigma max is sigma A prime plus sigma M prime. So NY is unknown. So let's see what we are given, what we are not given. We're given SC, we're given SUT, right here. We're given SY. Okay, we are not given S sigma A prime, sigma M prime, sigma A, sigma. So we only need to find sigma A prime and sigma M prime. Okay, we know sigma A and sigma and tau M, but we don't know what sigma A prime. So sigma A prime is sigma primes are the von Mises stresses. So to find sigma A prime, what we need to do is, and this is a formula in the formula sheet, it's sigma A square plus 3 tau A square, and sigma M prime is sigma M square plus 3 tau M square. So I think this completes the thing, which is sigma A is here, okay, and tau M is right there. So if we can find sigma A and sigma tau M, and of course tau A is 0 and sigma M is 0. If they're not given, they're assumed to be 0. So if we can find sigma A and tau M, then we have solved the problem. We are given sigma A bar and tau M bar. We only need to find the stress concentration factor due to fatigue. Okay. So let's start this way. Let's compute KFS, find sigma A tau M, then find sigma A prime, sigma M prime, and finally we'll find NF and NY. Okay, so in reverse. So let's start off with KF. So to find KF, we need to find the stress concentration factor due to this geometry. So that's something which will be given. In this case, I have the relevant stress concentration factor due to the fillet. This is the one that you need. So this is giving the stress concentration due to the fillet, but here it is due to the torque T. And then we need to get another one, which this one is due to bending momentum. Okay, so let's compute. So for this, we need to know a few ratios. We need to know R divided by D and capital D divided by D. So capital D divided by D is given to us 1.2. R divided by D is going to be R, which is, let's go back, R is 3, D is 30, and by the way, D divided by D is 1.2. So 3 divided by 30, which is 0.1. So D divided by 2, 1.2. So we are looking at this line.
Wait, remember that the question has those measurements in millimeters, but does that really matter?
It's a ratio of 2 units in millimeters. So if you have millimeters or millimeter, it's just going to be dimensionless. And then R divided by D is 0.1. So this is the one. So you need to go up here, find this. This is going to be the value. So I don't know, this I guess is 1.2. So it's somewhere between 1.2 and 1.4.
1.35, because I know it's not in the set.
Yeah, let's take 1.35. That looks like a good guess. Well, I took 1.38. I mean, anything in the range of 1.3 and 1.4 is fine. So I took it as KTS. And KTS is because it's torque. So the S is denoting shear. So 1.38. But 1.35, anything in this range, it's probably less than 1.4, but 1.4, 1.35 is good enough. Okay, so that's our value. Now let's find it for this geometry. Here again, D divided by 2 is the same, it's 1.2. So this is the 1.5 line. This is the 1.2 line. There's no 1.2, there's 1.1. And then 0.1 is here. Okay, so somewhere between this line and this line, this is the top, this is the lower boundary. This is 1.6. So I guess it's somewhere between 1.7 maybe the good guess. I have it as 1.62. But you can put any value from 1.6 to maybe 1.7 should be fine. So we found KT and KTS. We need to find KF, and to find KF or KFS, we need to find the Newberg constant. Okay, so the Newberg constant depends on the yield strength. So the ultimate strength, which is 700 MPa. And there's a formula in the book for bending. For bending, the Newberg formula is square root of A equals 1.24 minus 2.25 10 raised to negative 5, sorry, negative 3 SUT plus 1.6 10 raised to negative 6 SUT square 2.11 10 raised to negative 10 S cube, and then plugging in the value for SUT in that equation, you get square root of A is 0.308. There's another formula for torsion. that is something like this: 0.958 minus 1.83 10 raised to negative 3 SUT plus 1.43 10 raised to negative 6 35 SUT square minus 4.11. Let me check this. I think that might be wrong. Yeah, for torsion, it is 1 point. Yeah, it's negative 6, my bad. Okay, so that comes out to be square root of A equals 0.2367. Okay, so we've got square root of A, but we still have to find the notch sensitivity. So here's how we find notch sensitivity. It says a notch sensitivity for bending, and there's one for torsion. So let's do that. So the notch sensitivity for bending is 1 plus 1 square root of A square root of R, but R is the radius, it's 3 millimeters. So we write this as 1 plus 1 plus square root of A. We found the square root of A. By the way, this is for bending. So square root of A is 0.308. And so it comes out to be 0.849, which we can round up to 0.85. And then we can find the stress concentration for fatigue. It's 1 plus Q KT minus 1 equals 1 plus Q, which is 0.85. KT was found to be 1. Here KT was 1.62. One. Okay, so KF is 1.53. Okay, so we're done with that. Let's find QS due to shear, so torsion. QS is 1 plus square root of A divided by square root of R. So square root of A was, so that's again going back one page back, it's 0.2367 divided by square root of 3. It comes out to be 0.8798, which is approximately 0.88. So K, first this question. What lecture did you talk about von Mises stress, alternating stress sigma, and mean stress formula? I think I talked about von Mises stress for alternating stress in the chapter on, that's the 7th chapter. It was on shafts. Maybe I can open those notes after I'm done with solving this problem, but let me get to this question a little bit later. Okay, 3132. Okay, thanks. It is probably 3132, the last 2 chapters. So KFS is 1 plus QS KTS minus 1 plus QS is 0.88. KTS is, go back, it's right here, 1.38. Minus 1. So solving for KFS, we get 1.33. Okay, so we have finally computed KFS and KF. Now we can find sigma A, which is, sigma A, which is KF times sigma A prime. KF is 1.53. Sigma A prime is given to us. It's 60 MPa. So the stress is going to be in MPa, it's 91.8 MPa. Similarly, the shear stress is KFS sigma M prime. So it's 1.33. Sigma M bar is given to us, it's 80. And since it's an MPa, we have 106.4 MPa. So that gets us to finding the normal stress and shear stress due to alternating and bending loads. Okay. Now we can find the von Mises stress. So sigma A prime, this is the von Mises stress due to alternating load, is sigma A square plus 3 times tau A square, but the alternating shear stress is 0. So sigma A prime is sigma A, which is 91.8 MPa. Sigma M prime is sigma M square plus 3 tau M square, but sigma M is 0. So this will come out to be square root of 3 times tau M, which is 184.29 MPa. Tau 1 is 0 because it wasn't given. Yes, tau A is 0 because it's not given. So it's assumed to be 0. So those are the von Mises stresses. Okay, so we are now all set to compute the factor of safety with this information. So let's do that. Part A asks us to find the factor of safety using the D. Goodman equation, which is 1 divided by NF equals sigma A prime S E sigma M prime S U T. So 91.8 to 39 plus, which I'm just plugging in the values which I computed, 0.6454. So NF would be 1.55, and then B, the yield, we have NY equals SY divided by sigma A prime plus sigma M prime. So SY is given, it's 550. Sigma A prime and is 91.8. Sigma M prime is 184.29. And so we have 1.99.
First cycle yield, right?
No.
Or B. Is that what it says?
No. So the way this has to be found is, so this is how it is. So if NF is greater than 1, okay, then we say it's infinite life. Okay, in this case, NF is greater than 1. So you don't need to look further. If, however, if you see that NF is less than 1, then you need to check whether NY is greater than 1. If NY is greater than 1, then it's finite life. If it's finite life, then you can use that formula. What was that formula? to find the number of cycles, the SN formula. Okay, and then finally, if ny is less than 1, it's first cycle yielding. Okay, that's to say that the very moment you apply that load, whichever is given to you, you just break.
Like, we go back to the actual main question.
Sure. This is the question. Oh, yeah. State or not whether the part will yield on the first cycle, state whether or not part will have infinite life. So yeah, so the answer to the question is what? What do you think now, since I told you all the facts?
I saw first cycle yielding, and I can with respect to.
So the question asks you, will it yield, will it fail will it have infinite life, will it have finite life, or will it have first cycle yielding? That's the question. You can only have one of the three. So which one do you think is right? Is it infinite life, or it's finite life, or it's first cycle yielding?
Infinite, because NF is 1.55.
Right. So it will have infinite life. Since